Hello. So in this video, I'd like to talk a little about implicit differentiation. So the derivative is the slope of a tangent line. I mean, the textbook hasn't really emphasized that interpretation, but it is a true interpretation. I think for a lot of us, the first time we hear the phrase tangent line, we're talking about circles. High school geometry, maybe. And the slope of this tangent line ought to be the derivative at this point, but there's a problem. And that problem is that this circle is not a function, but the derivative is defined as the limit of functions, right? It's the limit of f of x plus h minus f of x all divided by h. The function notation is right there in the definition. So, question, how can we talk about the derivative at this point if the derivative is defined in terms of a function and the curve we're looking at isn't the curve of a function? Just to clarify, if it's been a while, the reason this is not a function is that we can draw a vertical line that hits the circle in twice, more than once. It flunked the vertical line test. Let's look at this concretely with an equation. X squared plus y squared equals 1. And we've got, or we'll state a specific point. Let's look at the square root of 1/2, comma, the square root of 1/2. This is a point on the circle. The square root squared is 1/2. 1/2 plus 1/2 is 1. And we can certainly draw a tangent line at that point. And let's ask for the slope of the tangent line at this point. So again, this isn't a function. We can't just dive in with the derivative. We instead use a trick called implicit differentiation. And I'm going to state, obviously very informally, that this trick is for when your x's and y's are mixed together, which is what we see up here with this equation, instead of what we're most used to, which is y equals an expression of x, our x's and our y's are mixed together. And the trick, or maybe I should say the method, is to differentiate both sides of the equation and to pretend that y is a function of x. So it's sort of, how do we deal with the fact that we don't have a function? We cover both ears and go la-di-law and pretend that we do. It's obviously possible to justify this in a formal mathematical way, but fundamentally, that's the answer. The way we deal with y not being a function of x is just refusing to acknowledge that fact and pretending that it is. But this has, when you do the differentiation, this little lie we're telling ourselves comes into play. So I'm going to take both sides of the equality, the x squared plus y squared, and the 1, and I'm going to differentiate both sides. And now there are 3 derivatives we have to take: x squared, y squared, and 1. X squared is easy, I hope. The derivative of x squared is 2x. The derivative of y of 1, sorry, is hopefully also pretty straightforward. The derivative of 1 is 0. What about the derivative of y squared? Well, if you're a little careless, you might say, well, the derivative of y squared is 2y, but hold on. If y is a function of x, and we have a function of x raised to a power, and we want to take its derivative, we have a tool for that, the generalized power rule. And the generalized power rule says, well, you use the power rule, you do get 2y, but then you multiply by the derivative of the function. And what is the derivative of y? I have no idea. This is the slope of the tangent line. This is exactly what we're looking for. This y prime, this derivative, is exactly what we want when we know what y prime is. When we know the derivative, we can plug in the point and answer the question. I guess anyway. So we want to solve for y prime. And just because there are plenty of examples in the textbook and, Creative Commons videos on Canvas, where solving for y prime is sort of algebraically tricky, I decided to make life easy on myself and select an example where solving for the thing we want is relatively straightforward. Subtract 2x from both sides, divide both sides by 2y. Minus 2x over 2y, a bit of simplification here. The x's cancel, and we get y prime equals negative x over y. And this is very common. When you do implicit differentiation, we expect both x's and y's in the derivative. Because suppose we didn't have x's and y's, suppose we only had x's. Well, the problem is that on this circle, we have the point, the square root of 1/2, comma, the square root of 1/2. But we also have the point, the square root of 1/2, negative the square root of 1/2. And it's just looking at this picture and just sketching in the tangent lines, you can see that they have different slopes. One of them has a positive slope, the other has a negative slope. So if the only thing we had in the derivative was an x value, we'd be in difficulties because x equals the square root of 1/2 isn't enough to tell us what the slope is. The slope could be negative, the slope could be positive. Now, when I give you both x and y prime evaluated at the point, the square root of 1/2, comma, the square root of 1/2. Now we have an x and a y, and it's negative x, the square root of 1/2, divided by y, also the square root of 1/2. So the slope of this tangent line is negative 1. And that's the idea of implicit differentiation. And we're going to use a very similar idea in an upcoming video called related, or upcoming topic, I guess I should say, called related rates, which you can sort of think of as implicit differentiation applied to word problems. But for now, signing off.